Hi everyone, welcome to the first episode of JEE Mantra Physics Recap. In this video, we will be having a quick revision through 4 chapters. Chapter 1, Electric Charge and Electric Field. Chapter 2, Electric Potential and Capacitance. Chapter 3, Current Electricity. And Chapter 4, Moving Charges and Magnetism. Alright, so these are the 4 chapters that I just mentioned. Alright, so moving to our first unit, that is electrostatics. All right, so here comes the very first slide for you. So here we are starting with the basic properties of charge. So out of the properties of charge, for us the most 3 important properties are these 1, 2, 3. First one is additivity, second one is quantization, and third one is conservation of charge. Additivity says if we have got a system that contains Q1, Q2, Q3, etc. up to Qn charges distributed at the different parts, then the total charge is going to be the summation of the individual charges distributed at the different parts. The only thing that you must take care of is while doing the summation of the charges, you must not miss the polarity. Coming to the second, that is quantization of charge, it says Q is equal to plus or minus n times E, where small letter e is the charge of electron, that is 1.6 into 10 to the power minus of 19 Coulomb. And here the polarity, whether it is has to be positive or that has to be negative, it totally depends upon whether the electrons were removed or whether the electrons is added. If it is removed, you are going to get the charge as positive, and if you are adding, you are going to get the net charge as negative. And comes the third one, that is conservation of charge. Basically it says that if your system is an isolated one, the total charge remains constant. In other words, you cannot create any electric charge or you cannot destroy any electric charge. So that was the basic properties of electric charges. And moving to the next, that is Coulomb's law in electrostatics. So here first of all we will be discussing Coulomb's law in the scalar form, and the next part we will be moving to the Coulomb's law in vector form. All right, okay, so here comes the first. It says if you have got 2 charges Q1 and Q2 which is separated by a distance of separation of small letter r, then the electrostatic force F suffix E is going to be K times Q1 Q2 all divided by r square. And what's K here? K is the constant of proportionality, and that is equal to 1 divided by 4 pi epsilon naught, and it is having the value as 9 into 10 to the power 9. All right, now the value of epsilon naught, which is also we can call it as what, the absolute permittivity of air or vacuum, that is having value numerically equal to 8.854 into 10 to the power minus of 12. Okay, so this is the case if you are having 2 charges separated by a distance small letter r, and the medium of separation is air. So this is the force by which they are going to interact each other. It could be either attraction or it could be repulsion depending upon the polarity. Okay, now instead of air, if we replace some replace air with some other medium, there epsilon naught is going to be replaced by epsilon naught times K, or epsilon naught times epsilon R, or epsilon naught. Okay, where this K term, this K, that is nothing, that is the dielectric constant, which is also called as relative permittivity. And how the relative permittivity of any particular medium is connected to the permeability of air or vacuum is permittivity of any medium upon permittivity of air or vacuum. That is what we call it as relative permittivity. That's also called as what, dielectric constant. For air, dielectric constant is 1, for water it is 81, and for metals that is infinity. All right, now comes the next. As I told you earlier, we need to discuss the Coulomb's law in vector form also. Fine, so here in this figure you can see 2 charges, that is Q1 as well as Q2, and this is of identical charge. I prefer to have it as positive. Now here this is force acting on 1 due to 2, and here this is force acting on 2 due to 1. I repeat, this is 1 due to 2 and here it is 2 due to 1. R1 is the position vector of charge 1 and R2 is position vector of charge 2. So in that case, force acting on 2 due to 1. I repeat, force acting on 2 due to 1 is going to be 1 divided by 4 pi epsilon naught. Alright, Q1 Q2 into R2 minus R1 is in vector form. I repeat, R2 minus R1 in vector form, all divided by R2 minus R1 the all cube. So that is the difference over here, because here we need to mark the direction. Okay, in the same way, if we consider F12, that is force acting on 1 due to 2, then it is going to be 1 divided by 4 pi epsilon naught again. Okay, Q1 Q2, you can see both the part are same. The only difference is going to be with this part. So if here, if it was R2 minus R1, in this case it is R1 minus R2, all divided by R1 minus R2 raised to power 3. Okay, based on that, I can come to an important conclusion, that is F12 vector that is equal to minus of F21 vector. You must not miss, all these are in vector form. That is why it is marked as bold letters. Alright, so this everything is in vector form only. So that's why in here I am specially marking that along with that vector symbol. Alright, okay, moving to the next, that is force between multiple charges. So just now we considered how the two charges can be repelled or attracted by the effect of each other. So if we are having a system that is containing more than two charges, then how we are going to calculate? So here I am having an example where Q1 charge, I repeat, Q1 charge is surrounded by Q2, Q3, Q4, etc. up to Qn. Then the net force experienced by that charge Q1, I repeat, the net force experienced by that charge Q1, that is going to be force acting on 1 due to 2 plus force acting on 1 due to 3 plus force acting on 1 due to 4, etc. up to force acting on 1 due to the nth charge. So that is going to be the net force experienced by the charge 1, where 1 is surrounded by, I repeat it again, charge 1 is surrounded by Q1, Q2, Q3, etc. up to Qn. Alright, so here you have got the expanded form of this one. You may refer that if you want to note down that in detail. Alright, the next is continuous charge distribution. I repeat, continuous charge distribution. Here we are going to deal with three different category of continuous charge distribution. First one is linear charge distribution, second one is surface charge distribution, and the third one is volume charge distribution. All right, so what is the significance of these three is, you know, the interactive force between two electrically charged bodies is not only studied just by considering the point charges, it can be due to continuous distribution of charges also. It's not mandatory that we can only study the interaction between two point charges. Okay, so the linear, extended charge distributions are also possible, but how they were behaving, it's totally different from the way the charges are being distributed. So that is why we are considering three different categories. So while considering that, the most important part is about the distribution of the charges. So if the charges are distributed linearly, for example, I am having a charge distributed along a length of capital L. All right, so if Q charges is distributed over a length of capital L, then and moreover, if the charge distribution is uniform, I repeat it, that if the charge distribution is uniform, then the total charge distributed Q upon total length, this is what we call it as what? Linear charge density. Okay, so whenever we are telling about the linear charge distribution, this particular term, that means linear charge density, is very, very important, because that gives us the idea how the charges are distributed, how closely the charges are distributed, or how far the charges are positioned. In that, in all informations can be collected in this way. And if the charge is distributed over an area, so we can say that Q, total charge is Q, total area is capital A. In that way, we can say that Q upon A, that is equal to surface charge density. And if charge is distributed over a volume, we can say that Q by V, that is equal to volume charge density, what? Rho. All right, now if the charge distribution is not uniform, I repeat, if the charge distribution is not uniform, in that case we will consider a small area, that is ds. All right, and we can consider the charge associated to that small area, that is dq. Then for that small area, again the same thing is considered, the same format is considered over here, but this time the area is limited, that's why we are going for ds. So obviously once area is small, charge is definitely going to be small, so that's why we are having dq here. In the same way you can have dq by dl is equal to lambda, and you can have dq by dv equal to rho. Again here this is volume charge density, here it is surface charge density, and here it is linear charge density. All right, so this is how we are going to give the information in most of the questions. If the charge distribution is not charge distribution is a linear charge distribution or surface charge distribution or volume charge distribution, this is how they are going to give you the information regarding how the charges is distributed. That means in terms of lambda, sigma and rho it is going to be. Next is electric field. All right, electric field. So electric field, you know that the space around any charged body within which another charged body is going to experience an electrostatic force of attraction or repulsion, that space we call it as what? Electric field. So the numerical importance of that electric field, we used to tell that in terms of what? Electric field intensity. It is represented by letter what? Capital E. So mathematically how we define that electric field intensity is limit delta q tends to 0 F upon q naught. Now what is this F? F is the force experienced by the charge q naught, and you must not miss this particular part, limit q naught tends to 0. That means q naught, which we consider it as a test charge, that is infinitesimally small. So a charge of q naught which is infinitesimally small, force experienced by that charge upon the magnitude of the test charge, that is q naught, that particular value is called as what? Electric field intensity. I repeat, electric field intensity. So the dimensional formula for electric field intensity, capital E, is ml t raised to minus 3 a raised to minus of 1. I repeat, ml t raised to minus 3 a raised to minus 1. And super important part is again electric field, that is a vector quantity. Information number 1. Information number 2 is the direction of the electrostatic field. The direction that is going to be the force acting on positive charge. What it is? Positive charge, which means if I have got a source charge capital Q here, and you are asking me to find out electric field at P, which means I must leave a test charge Q naught which is of polarity positive, and the force experienced by this test charge. So since this being positive, definitely this is going to be the electrostatic force repulsion. So the direction of the force experienced by this test charge, exactly the same is going to be the direction of what? Electric field. Okay, so that is a very important point, very important point. Moving to the next, that is electric field due to a point charge. How to calculate the electric field strength or electric field due to a point charge at a distance small letter r from the source charge, that is small letter q. So we are having a source charge small letter q, all right, and we are asked to find out electric field at point P, which is located at a distance small letter r from the source charge. So there the electric field is going to be capital E equals 1 divided by 4 pi epsilon naught q by r square. All right, q by r square, where q is the source charge and small letter r is the distance of separation. How to find out the direction, that we already discussed in detail, and this is the case where, I repeat, this is the case where the medium is air. The medium is air. In other case, the way the force was changing once the medium got changed, the same way capital E for a given medium, that is going to be 1 divided by 4 pi epsilon in terms of instead of epsilon 0 or epsilon naught, we are going to have epsilon here and q by r square. So here this is going to be for a given medium with permittivity epsilon, and there it's going to be for air. And the next one is, what if we are having more than one charges? Okay, there it was what, just q, and this time I am going to have q1, q2, q3, etc. up to qn. In that case, the way we consider the superposition principle while calculating the net force experience, in the same way we can have q1 here, q2 here, and q3 here. All right, so due to q1 it's going to be e1 here, all are positive, don't miss that, all are positive. Due to q2 it's going to be like this, that is e2, and due to q3 it's going to be E3 in this way. So the net electric field at this point, the resultant electric field or the net electric field at that point, that's nothing the origin, that's going to be capital E vector equals to E1 vector plus E2 vector plus E3 vector. And if you have got a provision where you are having n number of charges, the way I told you in the beginning, so that will what? That will keep on extending up to E, and the same is represented here in another format. All right, moving to the next, that is electric field lines. So how this particular topic is important in, like, as far as JEE part is concerned, there might be questions, or in the previous year questions, if you refer, you can come across the questions where the so the options may be like, definitely 4 options will be there, and there will be like some pattern of electric field lines will be represented, and they might be asking you to identify the correct one or the wrong option out of that. All right, out of the 4 you need to either find out the correct option or you need to find out the wrong option. So this particular piece of information is going to be really helpful for to get into that type of questions. So here the first hand information what I do want to share with you is, if I am having an electric field line like this, okay, so this is the direction of electric field, and so here in the second figure we can see the electric field lines marked in the same way. Okay, now if somebody is asking you to find out the direction of electric field at this point P and Q, then we must draw a tangent in the same direction of electric field. So here the electric field was going towards right, so I marked the point P, and the same direction of electric field line I just marked a tangent, and that tangent will give the direction of electric field here. So EP cap is going to be this. So here at Q, if I want to find out the electric field, it's going to be again a tangent in the same direction of electric field. So here this is going to be the direction of EQ cap. Information number 1. Here comes the second. The second information is, have a look. Here the relative separation between lines is R suffix A. That means the distance of separation between 2 nearby electric field lines is marked as R suffix A, and here the electric field lines between the distance of separation between 2 nearby lines is marked as R suffix B, and it's very clear R suffix A is less than R suffix B. If the relative separation is lesser comparatively, definitely then EA must be greater than E suffix B. So that is very important information, and this will really help you in such type of comparative questions. All right, moving to the next, that is properties of electric field lines. Again, this information is really going to help you in the type of questions that I just discussed related to the information that we had in the previous line. So here we are going to discuss about properties of electric field lines. Okay, so the first property is, it starts from positive charge and terminate on the negative charge. Information number 1. That means if you are having a figure where electric field lines is marked like this, so definitely you can mark this as a wrong option, because associated to the positive charge definitely electric lines of force must be originating from a positive charge, and that must be ending on to a negative charge like this. Okay, fine. I was just giving an example like how the questions can be expected based on that single point. And second one is they are never going to intersect each other. Two electric lines of force never intersect each other. And the third one is electric fields never form a closed loop. All right. And the fourth point is, okay, it's going to be continuous. I repeat, it's going to be continuous without any break if we have got a charge free region. This is again super important information. Okay, if you are having a charge free region, electric field lines are going to be continuous if it is a charge free region only. All right, fine. Moving to the next, that is electric field due to continuous charge distribution. While giving the intro of continuous charge distribution, I already told you the electrostatic interaction between two charged bodies. It's not mandatory that for that to happen the charged body need to be always a point charge. It can be continuous charge distributions also. So if we are provided with a continuous charge distribution, either it is linear charge distribution, surface charge distribution, or volume charge distribution, how to calculate the electric field? All right, so let's start with the general format of that. If I am having a point charge, then the electric field due to that point charge can be marked as capital E equals 1 divided by 4 pi epsilon naught, all right, Q divided by R square. I'm just telling about the magnitude only, direction is not considered here. And if I want to consider the direction, then if I consider this as a point charge, I repeat, if I consider this as a point charge, okay, and a positive one, I repeat, this as a point charge and again a positive charge, then it's going to be along the same direction of R cap, where point P is this and we are having charge Q, so it's going to be the direction like this. R cap is this, and the distance from the source charge to the point P where we need to calculate the electric field is marked as small letter r. Okay, and if it is a small charge, instead of small letter q, if it's a very small charge, then we calculate the electric field dE as 1 divided by 4 pi epsilon naught, okay, dq divided by r square, again r cap, isn't it? Yes. Now instead of dq, if we are provided with a linear charge distribution, then for a small length of dl, and for a small area of ds, and for a small volume of dv, dq is going to be lambda into dl. Here dq is going to be sigma into ds, isn't it? And here dq is going to be what? Rho into dv. So instead of dq, this term will be considered. You can see here it's 1 divided by 4 pi epsilon naught sigma ds divided by r square times r cap, and here it is 1 divided by 4 times integral of lambda into dl divided by r square into r cap, and here for volume charge distribution is 1 divided by 4 pi epsilon naught integral of rho into dv divided by r square into r caps. Integration symbols, I think you might be getting it right. Integration symbols means the summation of small charges. All right, small charges were there, so addition of that small charges altogether give the resultant electric field, that is ES for surface charge distribution, EV for volume charge distribution, and EL for linear charge distribution. All right, next is electric field of a ring of charge. That means we are having a ring, either it could be positively charged or it could be negatively charged, and regarding the ring we are having some specifications. Specification number 1 is the charge of the ring is, here it is positive and here it is minus of small letter q. Okay, information number 2 is the radius of the ring is capital R, so here also again it is capital R, and we are asked to find electric field at point P, which is at a distance of small letter x. Here also we are having point P, again that is at a distance of small letter x. So the general information in the both case, what I can share with you is that if capital E is treated as the electric field, then the electric field at distance x from the center of the circle, capital E, is going to be 1 divided by 4 pi epsilon naught q into x, all divided by x square plus r square, all raised to 3 by 2. Same thing you can have here as well. Okay, fine. X, we already know what is the distance. That x is the distance from the center of the loop towards the point P along the axis. Capital R is the radius and q is the charge. The only difference in both these two cases, if we compare, is if I am having point P here and the charge distribution is positive, then the electric field is going to be away from the center. It's going to be away from the center. If it is positive, it's going to be away from the center, because you just leave a positive charge there plus q naught. This positive charge will be repelling q naught. And if it is negative, definitely that q0, that is the test charge, is going to be attracted by this particular negatively charged ring. So if it is negative charge distribution, the electric field is going to be towards the center, and if it is a positive charge distribution, is going to be away from the center. All right, now comes a special cases, few special cases associated to the electric field due to a charged ring. All right, special case number 1. What if at x equal to 0? What if at x equal to 0, which means this particular point P, it is going to be shifted towards the center in the both case. Okay, in that case, definitely the value of x is going to be what? 0. And if value of x is going to be 0 in this given case, you can lock the electric field is also going to be 0. Information number 2, that is, what if x is very greater than capital R? X is very greater than capital R. In that case, what happens is, consider this equation. Consider this equation. X is very greater than capital R, which means x square plus capital R square is approximately equal to what? X square only. Now here this is going to be x square raised to 3 by 2, which will leave x cube only on the denominator. I repeat, only x cube in the denominator. Then this particular equation is going to be E equal 1 divided by 4 pi epsilon naught. I repeat, 1 divided by 4 pi epsilon naught q into x divided by x cube. This will cancel each other. That will leave x square in the denominator. Now comes the final expression as capital E is equal to 1 divided by 4 pi epsilon naught q divided by x square. And it is nothing, it's exactly the same mathematical relation that gives us the information regarding electric field due to a point charge q at a distance of small letter r. So this special case number 2, that says, if we are having a point P that is at a distance of x from the center of the circular loop, then the electric field capital E is going to be same as that of a point charge. That was special case number 2. And comes the third one, that is where we can have the electric field to be maximum for a ring of radius capital R and charge small letter q. So if we consider the distance from the center of the ring along positive x-axis direction or along negative x-axis direction, if capital R is the radius, then the electric field is going to be maximum at a distance x is equal to R divided by root 2. Okay, how to get that? I'm just giving you a hint. Just take the differential of dE by dx and put that equal to 0. It's nothing, it's a condition of maxima minima case. All right. Okay, so this is the graphical variation that it shows. I'm just showing it here in the positive x-axis direction only. If it is if you are considering the same in negative x-axis direction, you are going to have the mirror image of that in the quadrant number 3. All right, moving to the next, that is electric potential. We all know how to define electric potential, that is work done in bringing a unit positive charge from infinity to any given point, that is treated as electric potential at that point. So we define the mathematical relation as electric potential is equal to W by Q, and the SI unit is joule per coulomb, or that is also termed as what? Volt. All right, what about the dimension? It is ml square t raised to minus 3a raised to minus 1, and the most important part is here, this is a scalar quantity. This time it's not a vector quantity. So far from this chapter we discussed about the force, definitely that is a vector quantity, and post that we discussed about the electric field. There also it was that was a vector quantity, but here this time electric potential, that is a scalar quantity. All right, next is electric potential difference. Basically, as the heading, I mean the name the topic itself says, it's the difference between electric potential difference between electric potential between the 2 points. I repeat, it is the difference of electric potential between 2 points. Basically, if I have got point A and point B here, and V suffix A be the electric potential at A, that means the work done in bringing unit charge from infinity to this point is V suffix A, and to the other point is marked as V suffix B. And if VA is greater than VB, I repeat, if VA is greater than VB, then VA minus VB, that is what we call it as potential difference. At this time it's marked as positive because I already told you VA is greater than VB. And the same can be defined in terms of work, that is work done in taking unit positive charge from B to A. And if we are moving a charge of magnitude small letter q, then WB suffix A upon Q, that is going to be VA minus VB. All right, moving to the next, that is regarding the there we discussed about electric potential, and we discussed about the units, and all the same thing is applicable here as well. The unit SI unit, that is going to be again joule per coulomb, or volt capital V. It's represented as capital V. The unit is going to be the same. Then definitely the dimension is also going to be the same, that is ml square t raised to minus 3 a raised to minus of 1. Okay, now comes electric potential due to a point charge. Mathematically, that is going to be V equal to 1 divided by 4 pi epsilon naught Q by R. It is a scalar quantity, not a vector quantity, so direction is not at all important here. And if we are having a system of charges, I repeat, if it is a system of charges, then the net electric potential V is going to be V1 plus V2 plus etc. up to Vn if you are having n number of charges, where V1 is going to be 1 divided by 4 pi epsilon naught Q1 by R1, and V2 is going to be 1 divided by 4 pi epsilon naught Q2 by R2, V3 is going to be 1 divided by 4 pi epsilon naught Q3 by R3, etc., 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 where R1 is the distance to the point where we need to calculate the electric potential from the source charge, that is Q1, Q2, Q3, etc., in the same pattern. All right, so this is another format in which we can represent the general equation for n number of charges, like starting from, you can see that I starting from 1 to I equal to n. In that way also it is represented. So this is the simplest way, one of the simplest way in we can easily connect the same thing to this one. All right, moving to the next, that is potential gradient, and this is again a super important area, because if capital E is given, how to get the value of potential, and if V is given, how to get the value of electric field, in all those areas, this is going to be a really helpful information. So if V is electric potential, which is given as function of small letter r, then electric field capital E is going to be minus of dV by dr, minus of dV by dr. And the most important part is, you must know what is the significance of this negative sign given here. This negative sign says, it's very clear, if this be a positive charge, you know that electric field is from the origin towards right. I'm just considering this one, or here I can say that electric field is along this direction. Okay, from this source charge. Now if electric field is in the upward direction, let me mark 2 points, that is A and B. So electric field is from B to A. I repeat, electric field is from B to A. Then the electric potential will increase in the opposite direction. That means if electric field is from B to A, which means V suffix B, that means electric potential at B is definitely going to be greater than electric potential at A. So that is that negative sign indicates. Okay, and dV is the small change in electric potential, and dr is the small distance that dr for which dV change was observed. Alright, and altogether this dV by dr, I repeat, dV by dr, that is known as potential gradient. Alright, moving to the next, that is equipotential surface. As the name indicates, it is that surface where electric potential is the same. Electric potential is the same. Alright, so once electric potential is the same, so just because of that reason, if I mark this be an equipotential surface, and let me mark this as A and this as B. So here this is VA and electric potential at here this is VB. Now if I consider VA minus VB as work done in taking the charge from B to A upon Q. Obviously, since equipotential, since this being an equipotential surface, VA is equal to VB, so definitely this value is going to be what? 0. So once this value is 0, I can say that WBA is going to be 0. That means if we do have an equipotential surface and if you want to move charge from one point to another point on that surface itself, then the work done is going to be what? 0. Alright, so that is a very super important information that you must know associated to equipotential surface. More than that, still we do have point related to equipotential surface, and here comes the remaining point number 1. Point number 1, that equipotential surface, it could be a planar surface or it could be a solid surface. Alright, but most important part is it can never be a point sized. It can never be of a point size. Alright, next important information is the electric field lines associated to an equipotential surface are always perpendicular. Okay, so if somebody is saying that this be an equipotential surface and this is electric field line associated to that, that means that is not at all possible. Alright, next point is if we are having a isolated point charge, the shape of the equipotential surface associated to that source is going to be spherical. That is going to be spherical. And if you are having a uniform electric field, then the shape is going to be planar. Okay, and if you are having a line charge or linear charge distribution, then the shape of the equipotential surface is going to be what? Cylindrical. Alright, moving to the next, that is motion of charged particle in electric field. This area is very important regarding, the path of the charge traveled by a charged body that is getting entered into an electric field. Sometimes at what angle they will be coming out of the electric field. Okay, what will be the distance traveled, how how the charged particles are relatively moving, like how the distance of separation might be. So possibilities are like much more associated to this, like to generate questions from this particular area. So again, this is an area of great importance, I mean a greater weightage, in fact, I can say. So few information that we must know about this one is, first thing, as you all know that if we have got a charge small letter q placed in an electric field of capital E, the force experienced by that charge is going to be F is equal to Q into E. Alright, now what is going to be the acceleration experienced by the charged particle? So in this entire case, what I am telling you is, my charge that I am considering here, that is having initial velocity as u equal to 0. Alright, u equal to 0, definitely. So since F is equal to Q into E, the acceleration experienced by the charged particle is going to be force divided by mass, that is Q suffix E upon M. This is going to be the acceleration. Okay, now if that particular charged particle is allowed to be in the electric field for a time duration of small letter t, then it is going to attain a final speed or final velocity v is equal to what? A into t. Alright, so since we know the value of a from here, alright, we can have the final expression for velocity as v is equal to qet divided by small letter m. Alright, now here this is nothing, this is represented in some another way. Alright, that is nothing, we are provided with the potential difference of capital V. So here the electric field is now being replaced by some other terms, that is capital V is considered there. Alright, in that a case the same value, that means the speed attained by this charged particle is going to be what? Under root of 2 times q into delta v upon m. Under root of 2 times q into delta v by m, where delta v is the potential difference through which this charged particle got accelerated. Alright, okay, now what about the momentum? What about the momentum? We all know that momentum P is equal to m into v. If we get the expression for v from this particular slide, okay, if we can substitute the expression for v from here, the momentum attained by the charged particle P, okay, the momentum attained by the charged particle P is going to be P is going to be m into under root of 2 times q, let me write it at some other space, m into the same thing only, under root of 2 times q delta v upon m. Okay, so cancelling that m terms again, we can have the final expression as under root of 2 times m into q into delta v. I repeat, this is the expression for linear momentum. So here we had the expression for velocity, alright, okay, and here we are having the expression for linear momentum. Here we had the expression in terms of electric field capital E and potential difference. Here again we are having the expression for linear momentum again in terms of what? Electric potential. And comes the last one, that is the kinetic energy. Okay, so we know that if the charged particle is allowed to accelerate it, okay, in an electric field, or you can say that it's allowed to accelerate through a potential difference of delta v, finally it is going to have a non-zero value of speed, so definitely it's going to have a kinetic energy. So the kinetic energy K, that we all know that is going to be half of m into v square. So here in this expression we have got the expression for v in terms of electric field, and we have got the expression for v in terms of the electric potential. So the same thing is considered here. So finally I have got the expression for electric energy, kinetic energy as q square e square t square divided by 2m if it is considered in terms of electric field, and it is half of m into 2 times q delta v upon m if it is considered in terms of potential difference. So here this m and m will cancel each other, so that's going to be q into delta v. Q into delta v. Again, work done, you remember, work done upon charge, that was what? Potential difference. So work done is going to be delta v into q. Delta v into q is the work done, and the same work done is stored as the kinetic energy. Can connect again this. Was that okay? Moving to the next, that is electric flux. The electric field lines perpendicularly linked with any given surface is known as electric flux, represented by the letter phi suffix e, isn't it? So the unit is m square per coulomb. All right, and how we have the mathematical expression is phi suffix e, that is e dot ds, or it's going to be e into ds times cos theta, where this is ds vector and here this is electric field E and this angle is theta. All right, so this is the general expression for electric flux, d suffix phi. All right, okay, now moving to the next, that is Gauss theorem. All right, obviously you know that electric flux Gauss theorem, again this is an area of greater weightage. So let's see what is Gauss theorem. Gauss theorem says that if we have got a Gaussian surface, all right, then the total flux linked phi suffix E is 1 divided by epsilon naught times the total charge enclosed. Okay, fine, and that means we can represent it in the same way in this, I mean we can represent in some other format also, that is closed surface integral of E dot ds, that is equal to 1 by epsilon naught times the total charged enclosed. Both are the same. All right. Now, yeah, I missed that part. See, this is again a very important information. So let me consider a cubical Gaussian surface like this, and let me have a charge exactly placed at the center. So the total flux associated to this one, phi suffix E, that is 1 by epsilon naught time the charge enclosed, is how much? It's Q. Okay, and this particular cubical Gaussian surface has got 6 surfaces. So what is the flux associated with any one of the surface? Let me consider the very topmost one. So definitely the flux linked with that single surface, phi 1, that is going to be Q divided by 6 times epsilon naught. So this was again, you know, you may come across this type of question frequently in your previous year question banks. So you must be able to know how to deal with that. So the multiple versions available are, you can have it somewhere at the corner, or you can have it somewhere at the exactly center of any one of the side, like that. Okay, so in that way multiple versions of the same is again available in your previous year question banks also. Now again, the next is like we are moving to the application of Gauss theorem. So here comes the first, that is electric field intensity due to an infinite long charge distribution. All right, so there electric field is going to be E is equal to 1 divided by 4 pi epsilon naught 2 lambda by R, or this can also be represented as 1 divided by 2 pi epsilon naught lambda by R. You may have the same here, where lambda is, you know, this linear charge density. And here comes the next, that is due to an infinite plane sheet of charge. Okay, fine. So if you are having a plane sheet, thin plane sheet of surface charge density sigma, then the electric field E is going to be what? E is going to be sigma divided by 2 times epsilon naught. How to find out the direction? That I already told you. If this is a positive charge, just keep a positive test charge over here. Test charge, I already told you, it's need to be a positive one, so it's going to be repelled by like this. So if I am having a surface charge distribution like this, though it look like a linear charge distribution, you must know this is a two-dimensional figure. Fine. So the electric field is going to be towards right here, and this is going to be towards left here as well. So because again, you know that if you drop a test charge here, then definitely that is going to be repelled by this source charge distribution. That is information number 1. So mathematical expression. And another part is, in this expression, that means electric field due to a thin charge distribution, you can't find a small letter r term anywhere here. Which means what? Which means the electric field associated to this particular charge distribution, that means a thin charge distribution, that is not depending on the value of small letter r. In other words, we can say that the electric field associated to this is always going to be a uniform electric field. So if we represent this using field lines, the distance of separation between the electric field lines must be same, and they must be parallel to each other. That is again a very, very important information associated to electric field of plane sheet charge distribution. All right, moving to the next, that is electric field and electric potential at a point on the axis of a uniformly charged ring. Electric field we already discussed. Now the same mathematical expression you can have it here, but while coming to the electric potential, there it's going to be 1 divided by 4 pi epsilon naught q upon x square plus a square raised to 1 by 2. There it was 3 by 2, and there q term was there, here q term is not at all there. That's the difference. You must be able to correlate each other. That's why separately I considered both the terms E as well as V here in the same slide. This is at a distance of x from the center. This is at a distance of x from the center, and capital R is the radius, and the total charge distribution over here, it's considered as Q. All right, moving to the next, that is electric field potential due to a charged spherical shell. It is a shell. That means the charge distribution is on the outer surface and the inner space is hollow. Okay, there the electric field at any point outside. So what I am going to do is, I am going to travel from here towards the center, and I'm going to reach after reaching point O only, that means the origin. So first of all, I am located at a position somewhere here, so that is where small letter r is greater than capital R. This is the case. Small letter r is greater than capital R. So the air there, the electric field is going to be exactly same as that of a point charge, isn't it? See, 1 divided by 4 pi epsilon naught q by r square. Alright, and what about the electric potential? 1 divided by 4 pi epsilon naught q by r. Fine, which means if we are having a shell, and if you want to find out the electric field, or if you want to find out the electric potential, then the mathematical relation is going to be exactly same as that of electric field due to a point charge at a distance of small letter r, okay, or electric potential due to a point charge at a distance of r. So it can be, so which means if you are having a point outside, then we may assume the entire charge is concentrated at the center somewhere here. Okay, fine, and we calculate the electric field as well as electric potential same as that of a point charge for small letter r greater than capital R. Was that okay? Next, if the point is at the surface, I told you our journey starts from here and now it's going to be somewhere here. Alright, it's going to be the same only. Again, it's going to be the same only. Let's have a look. If small letter r equal to capital R, again, what was the electric field due to point charge? It was 1 divided by 4 pi epsilon naught q by small letter r square. Now you have to just replace small letter r with capital R. That's all, is equal to 1 divided by 4 pi epsilon naught capital Q by r square, and V is going to be 1 divided by 4 pi epsilon naught q by capital R. That's all. Okay. Next, if we are having point inside, there you need to be a bit careful. If you are considering electric field, just try to recall Gauss theorem. Okay, this time if I am having a surface here, you don't have any charge distribution inside. I repeat, you don't have any charge distribution inside, which means the charge enclosed by this Gaussian surface is 0, which means electric field E need to be equal to 0. Now, while calculating the electric potential at any point inside the sphere, the shell, we were consistently doing work to bring that charge Q from infinity to till this point. We were doing just work because we were experiencing some force. Okay, and once we cross this particular surface and once we enter into any of the point inside the shell, now there is no electric field, which means we need not to upspend any more energy because there is nobody to oppose our motion. That means we need not to spend any amount of energy to move to any of the point inside the spherical shell, which means what is the work done to bring charge Q from infinity to any point on the surface, it will remain unchanged at any point inside the shell, which means what was the electric potential at the surface of the shell, the same is going to be the electric potential at any point inside. So it's going to be the same at any point inside, and electric field is already 0, and I told you why it is 0 as well. Alright, moving to the next, that is electric field and potential due to a charged non-conducting sphere. This time it is a non-conducting sphere, and you must understand here the charge distribution is considered as uniform charge distribution. So here the electric field is going to be electric field intensity for any point small letter r outside. Again, we can take it as the entire charge concentrated at the center, and while calculating the electric potential also we may consider the same. That's why you can see that E is equal to 1 divided by 4 pi epsilon naught q by r square, and V is equal to 1 divided by 4 pi epsilon naught q by r. Again, on the surface, exactly in the same pattern that we had for the case of the shell, exactly the same thing appear here. The only difference is for any point inside. There, the electric field E, that is going to be this time 1 divided by 4 pi epsilon naught q small letter r divided by r cube. And for electric potential, that is going to be 1 divided by 4 pi epsilon naught into q times 3r square minus small letter r square all divided by 2r cube. That is any point inside which is at a distance of small letter r. I repeat, I am going to give you a small briefing about that. Here this is capital R and we are having point small letter r somewhere over here. I think you will be able to connect it now. Now comes the last, that is at the center of the sphere where small letter r is equal to 0. You need to just substitute the value of small letter r over there. You will get the expression. Definitely E is going to be 0 and capital V is going to be 3 divided by 2 times Q divided by 4 pi epsilon naught into capital R. Was that okay? So that was electric field and electric potential due to shell and due to a solid non-conducting uniform charge distribution as well. All right, now moving to the next, that is due to a electric potential due to spherical shell. There that was a thin shell and here we are having a considerable difference in the area. The inner radius is small letter a and the outer radius is small letter b. I repeat, inner radius is small letter a, all right, and the outer radius is small letter b. All right, now let's see how it need to be considered. If we are having a point P at a distance like small letter r greater than capital R, small letter r greater than capital R. So this time what happens, we are having electric potential Q1, the charge distribution at the inner surface is Q1 and the outer surface is Q2. Then the value of electric potential V, that is going to be 1 divided by 4 pi epsilon naught Q1 plus Q2, Q1 plus Q2 divided by distance of separation is small letter r. All right, and if it is at somewhere here, if it is somewhere here at any point this way, all right, then we will calculate the electric potential as V is equal to, the point is now inside. Okay, now that is going to be 1 divided by 4 pi epsilon naught Q divided by B. This is due to the outer one, Q2 divided by B, due to the outer shell, and due to the inner one, that is going to be 1 divided by 4 pi epsilon naught Q1 divided by small letter r. You can see that here. Okay, and if it is again inside, like if you are having the case somewhere inside this here, that means small letter r this time, here small letter r is less than a. All right, then we are going to have the expression as V equals 1 divided by 4 pi epsilon naught Q1 divided by A plus 1 divided by 4 pi epsilon naught Q2 by B. No need to worry about like how to memorize all these things. For any point inside the shell, okay, I repeat, for any point inside the shell, it is going to be same as that of point on the surface. It's very easy to remember that. Exactly the same thing is happening here. We had a point in this case, we were having the point inside B and at a greater distance, outside sphere, the point was somewhere here, which was greater than small letter a and less than b. So due to the bigger one of radius small letter b, it's going to be same as that on the surface of B only. All right, and here in this case number 3, the point is A is less than A. That means electric potential due to the inner shell on the surface, that is 1 divided by 4 pi epsilon Q1 by A, and electric potential due to the bigger one on the surface, that is 1 divided by 4 pi epsilon Q2 by B. It is as simple as that. So if you are having any point inside, the electric potential is exactly going to be the same as that of electric potential on the outer surface. And if you are having any point outside the surface, then we will assume that the entire charge is concentrated at the center and we need to consider this distance small letter r. Okay, I am going to give a small briefing based on this because I don't want you to put that great effort to memorize this. Now let me have charge Q1, radius is r, radius is small letter a, and I am going to have a point small letter r here. So the electric potential due to the first one, V1, that is going to be 1 divided by 4 pi epsilon naught Q divided by, I'm not going to have small letter a, I need to consider it as small letter r, because my point is outside the shell. Now let me consider another one. Okay, and here this is charge Q2 and the radius b, small letter b. Now this point is inside. Once this point is inside, the value of V2 over here, that is going to be 1 divided by 4 pi epsilon naught. The charge associated with this one is Q2, and the distance, I mean the radius of this one is small letter b. So on the surface, what the electric potential, exactly the same must appear for any point inside. The same thing is considered here. All right, so don't consider it as that a difficult one. It's again a very simple thing only. All right, now moving to the next, that is potential energy of charged system. Here in this case, I am considering two charges, that is Q1 and Q2. They are separated by a distance of small letter r. Then the electrostatic potential energy is 1 divided by 4 pi epsilon naught, 1 divided by 4 pi epsilon naught Q1 Q2 divided by r. All right, and if you are having a system where three charges are there, like Q1, Q2 and Q3, Q1, Q2 and Q3, three charges are there. In that case, the combination is of 1 2, 1 3 and 2 3. Okay, and if you are having four charges, 1 2 3 4, so the combination is going to be of 1 2, 1 3, 1 4, 2 3, 2 4. 1 2 1 3 1 4 2 3 2 4. It's like this: 1 2 1 3 1 4 2 3 2 4 and finally 3 4. All right, 2 3 2 4 and one more is there, 3 4. Fine. So the same thing you can consider here. So for three charged particles, Q1 Q2 upon R12. All right, then Q2 Q3 upon R23 and Q3 Q1 upon R13. All right, where R12 is the distance of separation between Q1 and Q2, R13 is the distance of separation between Q1 and Q3, and R23 was the distance of separation between Q2 and Q3. All right, so similarly, if you are having four charges, we need to consider all the possible combinations of two pair each. Repetition need to be avoided. That's why I recommend this method to find it out. Next is potential energy in an external field. That means if I consider this Q1 Q2 or Q1 like Q1 Q2 or Q1 Q2 Q3 to an external field where capital E is the electric field, then the electric potential energy of the system is going to be. So here I am going to just consider a case where I am having only two charges, that is Q1 and Q2. Okay, so definitely due to their individual presence, there will be an electrostatic potential energy, that is Q1 divided by 4 pi epsilon naught, Q1 Q2 divided by R12. Definitely that need to be considered. In addition to that, our charge is now present in an external electric field. Due to some other source, we have got an electric field over there. So definitely there will be an electric potential value. So the point where the charge Q1 is located, if V1 is the electric potential, then we need to consider that potential where charge Q1 is located. So V1 into Q1 plus the electric potential at point where Q2 is located, that is V2 into Q2. So the net electrostatic potential is going to be V1 into Q1 plus V2 into Q2 plus Q1 Q2 1 divided by 4 pi epsilon Q1 Q2 all divided by R12. I repeat, V1 was the electric potential at where the charge Q1 was located, V2 was the electric potential at where the charge Q2 was located. Okay, then the total electrostatic potential energy of the system, that what we have in an external electric field, is V1 into Q1 plus V2 into Q2 plus 1 divided by 4 pi epsilon naught Q1 Q2 divided by R12. That means the electrostatic potential energy of that individual system where two charges were considered separately. All right, moving to the next, that is electric potential energy of collection of more than two charges. We already discussed this the previous slide, so no need to repeat that. Here you are having that four charge combination. See, 1 2 3. All right, so 1 2 3 4. Fine, the combination is going to be 1 2 1 3 1 4, 1 2 1 3 1 4. All right, then 2 3 2 4, 2 3 2 4, and after that 3 4. 3, 4. See, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Exactly the same. Alright, moving to the next, that is electric dipole. If we have got two charges separated by a finite distance of separation, that is known as an electric dipole. Okay, the most important physical quantity associated to an electric dipole is its electric dipole moment. That is a vector quantity, and that is going to be from negative charge towards the positive charge, and the dipole moment P vector is represented as Q. That is the magnitude of any one of the charge multiplied by the distance of separation, that is what? 2a, and that is supposed to be from the negative to the positive. And if I can mark this as 2a already, fine, this is going to be 2a cap. Distance of separation, that means I just want to mark the direction that's going to be from negative towards the positive. All right, fine. Next is electric field intensity and electric potential due to an electric dipole. Okay, now first is along the axial line. Axial line means let this be the negative charge and let this be the positive charge, and the line joining the center of this is known as axial line, and the line that I can create perpendicular to this is known as equatorial line. Here this is equatorial line, and here this is axial line. Alright, now if we consider the electric field, first of it is electric field along the axial line, that is 1 divided by 4 pi epsilon naught 2p times r all divided by r square minus a square all square, where small letter r is the distance from the center towards the point P where we need to calculate the electric field. And if we are provided the small dipole, in other words we can say that small letter r is very greater than 2 times a, that means the length of the dipole, then special case is applicable. That will take us to the expression, that is the electric field is going to be 1 divided by 4 pi epsilon naught 2p divided by r cube. And the most important part is you must know in the axial line, on the axial line, the electric field is supposed to be in the direction of dipole moment. So here the dipole moment was from negative to positive, so the electric field is also supposed to be in the same direction. Okay, and what about the electric potential? Electric potential, if we consider at any point on the axial line, that is going to be 1 divided by 4 pi epsilon naught p divided by r square minus of a square. You must be able to compare this particular expressions, and while comparison happens, you can see here small letter r was there, so here small letter r is missing. All right, and here the power was 2, and here the power is unity, and this power is 1. All right, the same thing is applicable here also. If small letter r is very greater than capital R, so you all know that r square minus a square is approximately equal to r square only. So that is how it's minor change over the expression of electric potential in case of capital V here. All right, moving to the next, that is on the equatorial line. I already told you what stands for the equatorial line. So if we calculate the electric potential, there E is not electric potential, electric field, I'm sorry. Electric field here, this is going to be 1 divided by 4 pi epsilon naught times P divided by R square plus A square raised to 3 by 2 at any point along the equatorial line. And you must not miss one point over here. Here, in case, in case of electric field along the axial line, we had the electric field in the same direction of electric dipole moment here. But here, in case of any point on the equatorial line, here the electric field is going to be in the opposite direction. Opposite direction of what? Dipole moment. So that point must not be missed. And if small letter r is very greater than capital R, again that special case need to be applied here also. So r square plus a square, definitely r square plus a square is going to be r square only. So here comes the modified version in the special case, that is E is equal to 1 divided by 4 pi epsilon naught p divided by r cube at any point on the equatorial line. And while coming to the equipotential, while coming to the potential calculation along any point on the equatorial line, so you know that here I have got a negative charge, here I have got a positive charge, where I have got a positive charge, here I got a negative charge, here I have got a positive charge, and both are having same distance at any point on the equatorial line. So definitely V value should be what? 0, isn't it? Moving to the next, that is at any point on line making an angle theta with the dipole. Okay, so what does basically it mean is, here you are having the dipole negative charge of the dipole, here I am having the positive charge of the dipole, and let this be the center, and I am having the point P here where we need to calculate the electric field or electric potential, and this is the direction of dipole moment, that is P, and this angle is theta, and here this is R vector. Capital P is the point where we need to calculate the electric field or electric potential, and from the center of the dipole towards that point P, small letter R vector is the distance, the exact position of point P. So in that case, I can have the expression for electric field capital E as, electric field is going to be 1 divided by 4 pi epsilon naught, okay, P into root of 1 plus 3 times cos square theta all divided by R cube if it is electric field, and if it is electric potential, then V is going to be 1 divided by 4 pi epsilon naught P cos of theta all divided by R square minus A square cos square theta. Alright, and again here also that special case is applicable, that means if small letter r is very greater than 2a. Alright, again you know that r square minus a square or r square plus a square is going to be r square only, so you can have a modified version as V is equal to 1 divided by 4 pi epsilon naught 1 divided by 4 pi epsilon naught P cos theta divided by r square in that case. Alright, moving to the next, that is torque on dipole in a uniform external electric field. The torque experienced is tau is equal to P cross E, and the maximum torque is P into E. It's nothing, it's the version of P sin theta, that's all. Okay, so torque experienced tau vector, that is what? P cross E. Alright, next is, what about the potential energy of dipole in uniform electric field? So if you are having a dipole and that is turned from an angle theta 1 to theta 2, theta 1 to theta 2 means initially that dipole was making an angle theta 1 with respect to electric field. So dipole making an angle means basically it is the angle made by the dipole moment with respect to the electric field. So initially the dipole moment was making an angle theta 1 with respect to the electric field, and later on it was aligned to another angle, that is theta 2 with respect to the electric field. In that case, the work done W is going to be minus of P cos theta 2 minus cos theta 1. That can also be represented as PE into cos of theta 1 minus of theta 2. Both are the same thing only. Okay, and what about the electrostatic potential energy of a dipole that is kept at an angle theta? I repeat, of a dipole that is kept at an angle theta, dipole moment P, electric field E, angle is theta, then the energy of this particular dipole is going to be minus of PE cos theta. That is going to be the electrostatic potential energy associated to an electric dipole kept at an angle theta with respect to the electric field. Next is dielectric constant. We already told about this dielectric constant, isn't it? Permittivity of any medium upon permittivity of air or vacuum, that we consider as was dielectric constant. All right, next is electric susceptibility, psi suffix E, and polarization capital P. So how they are connected is capital P is equal to psi suffix E into capital E. All right, and here comes another relation, that is relation between dielectric constant and electric susceptibility. So K is equal to what? K is equal to 1 plus psi suffix E. All right, next comes the capacitor. Capacitor is nothing, it's an arrangement to store the charge for any particular conductor which has got a charge of Q and it has got an electric potential V. Then the measure of its capacity to store electric charge, that is its capacitance, C is equal to what? Q divided by V. I repeat, it's Q divided by V. All right, and if I am having a spherical conductor whose radius is capital R, and then in that case the electric capacitance of that spherical conductor C is 4 pi epsilon naught times K into capital R. And if I have got a medium where the dielectric constant is K, and if the same spherical conductor is surrounded by air, then C is going to be 4 pi epsilon naught times capital R. That means we need to consider the value of K is equal to 1 over there. And if we are having a parallel plate capacitor, that means one plate is like this and another plate is like this. Area of this plate is capital A. Distance of separation between this is small letter d, and I have got a dielectric K filled in between. Okay, then the capacitance of this arrangement, that is going to be epsilon naught AK by D. Epsilon naught AK by D. And if it is air, definitely K is going to be 1. So in case if the medium is air, then it's going to be epsilon naught A by D. Was that okay? Moving to the next. What if in case here I completely filled it with dielectric, but in this case you can say that it's not completely filled. I have got the dielectric only for a limited length or limited thickness, small letter t. Alright, again the distance of separation is going to be the same, that is small letter d. Dielectric is of dielectric constant K. Alright, area of the plate is what? Again capital A only. In that case the capacitance C is going to be epsilon naught A all divided by, I repeat, epsilon naught A all divided by d minus of t plus t by K. Alright, moving to the next, that is what about the force of attraction between a parallel plate capacitor which is charged to a value of capital Q, area of the plate is capital A, and the medium of separation is air. In that case the force experienced is F is equal to Q square divided by 2 times A into epsilon naught. Alright, okay. Now next is, what if a dielectric slab is placed between the capacitor, okay, what will be the charge induced? Okay, in that case the charge induced is going to be Q dash equals Q into 1 minus of 1 by K. That will be the induced charge on the surface. Alright, now next is combination of capacitors. If I have got, like in this case, yes, I am considering n number of capacitors. So if I have got C1, capacitor of capacitance C1, C2, C3 like this connected in series, then the C equivalent of this one, how I calculate the C equivalent is, in series combination 1 by C equivalent is going to be 1 by C1 plus 1 by C2 plus 1 by C3. And if you are having n capacitors connected in series like this, the same formula will extend till C suffix 1 upon C suffix n. Alright, and what if it is a parallel combination? If it is a parallel combination, then C equivalent, it is going to be C1 plus C2 plus C3 etc. up to Cn it is going to. Okay, next is, what about the potential energy stored in the capacitor? We can have 3 equations related to the energy stored in the capacitor. One is in terms of V and Q, another is in terms of C and V, and another in terms of Q and C. Okay, so the first one is U is equal to half of Q into V. I repeat, half of Q into V. Next one is half of CV square, and the third one is Q square by 2C. I repeat once again, it is half of QV, second one is half of CV square, and third one is half Q square by 2C. Alright, next is energy density. Energy density means energy stored per unit volume, and I repeat, energy stored per unit volume of the space between the 2 parallel plate capacitors. Then the expression for energy density is calculated as half of epsilon naught into A square. That's going to be the energy density. I think, yes, here we have the complete expression. Alright, so it's going to be half of epsilon naught into A square. The same thing you can have it over here. Here this particular information gives how the energy density is being calculated. It's nothing, total energy divided by total volume. You can calculate the total energy stored in the capacitor just divided by the volume of the capacitor space between the, volume of the space between the capacitor plate. You will get exactly the same space over here. And here comes the next, that is redistribution of charges. Alright, redistribution of charges. Redistribution of charges means nothing. I am having a capacitor, okay, whose capacitance was C1. It was charged to a potential of V1. Now it holds a charge of Q1. capacitor of capacitance C1, it was connected across a potential V1. As a result, now it has got a charge of Q1. And now I have got another capacitor that is of capacitance C2. This time it was connected across a potential difference V2. Sorry, it was connected across a potential difference of V2, and then it got a charge of how much? Q2. Now we are going to connect this parallelly like this. I'm going to connect it in this way. Okay, so C1 and C2 are now parallelly connected. Now the charge exchange will take place between these two capacitors until that attains a common potential, and that common potential V is going to be C1V1 plus C2V2 all divided by C1 plus C2. All right, now doing so, this particular capacitor combination is going to lose some energy value, and the energy lost is going to be half of C1 C2 into V1 minus of V2 the all square divided by C1 plus C2. So this is going to be the total energy loss, and that will appear as heat across the connecting wires. All right, and next is what if n number of drops are allowed to collide or collapse to form a single drop of a bigger radius. All right, so here we are having small letter n small drops. Each of capacitance smaller is capital C, and it is charged to potential of capital V with charge small letter q. Okay, and surface charge density is marked as what? Sigma, and the potential energy capital U, okay, once it forms a single drop is, okay, just have a look. For the new drop, the total charge is going to be n times q. All right, now the electric potential of that bigger drop, that is going to be n raised to 2 by 3. I repeat, n raised to 2 by 3 times V. That was the electric potential of that single drop. And the total potential energy, once it forms the single drop, once it get converted into a single drop, I repeat once again, small n number of drops were there, they combine to form a single drop. All right, so here is the total charge after that getting converted into a single drop, and here this is the net electric potential that once it get converted into a single drop, and here comes the total potential energy, that is going to be n raised to 2 by 3 times U. All right, what about the capacitance? About the capacitance, it is the resultant capacitance is going to be n raised to 1 by 3 times capital C, and the surface charge density is going to be n raised to 1 by 3 times charge density sigma. Now let me take you to the next chapter, that is current electricity. All right, here comes the first topic of that is electric current. We all know that electric current I, that can be written as dq by dt if we are having an unsteady flow of current. Okay, I repeat, an unsteady flow of current. This is the expression for instantaneous current. And if we are having a steady flow, that means equal charges are being transmitted in equal interval of time, then I may have instantaneous current equal to average current, that as q divided by t, where t is the time in which q amount of charge got transversed across the cross section of a given wire. And if we are having a case where a charge of magnitude q is moving in a circular path like this, and the frequency of that motion is marked as small letter f, in that case we can have the expression for current as I is equal to q times f. Here comes the next, that is thermal velocity of free electrons. We all know that if we consider a conductor that has got a large number of free electrons, and once the temperature of that particular conductor is any value greater than absolute temperature, that means they are going to be in random motion, and that means the average speed, I repeat, the average speed by which these electrons are in random motion is approximately 10 to the power 5 meter per second. So if such an electrons keep on moving like this, obviously they will be colliding with the nearby electrons or the atoms. So if this is considered as two successive collisions, so this particular distance traveled by the free electron is known as what? Mean free path, and that is represented by the letter lambda. And if the RMS speed, I mean the average speed, that is termed as root mean square speed, that is marked as VRMS. Then the time gap between two successive collisions, that is known as the relaxation time. That relaxation time is going to be what? Lambda divided by VRMS. Moving to the next, that is drift velocity. We all know that once we apply a potential difference, in addition to the random motion, the electrons will be moving in the opposite direction of applied electric field. Okay, along with the random motions, the electrons will be shifting in the opposite direction of applied electric field. Now, the average velocity by which that shifting is taking place is known as the drift velocity, and the general expression of drift velocity V suffix d, that is equal to E times capital E into tau divided by m, where small letter e is the charge of electron, capital E is the electric field, and tau is the relaxation time. Again, m stands for the mass of free electrons. And if we want to change, I repeat, if you want to change this same expression in terms of the applied potential difference, then you may have the expression for drift velocity as V suffix d is equal to E into capital V times tau all divided by m into L. So you have got two expressions for drift velocity, that is this one as well as this one. Okay, now if you want to express the current flowing across the conductor in terms of drift velocity, then that expression I, that is equal to what? N into A into V suffix d times E, where N stands for number of free electrons per unit volume, A stands for the area of cross section, again V suffix d, that stands for drift velocity, and E is charge of electron. All right, moving to the next, that is current density. All right, the first thing I want to tell you is that current density is a vector quantity. It is a vector quantity, and the direction of that vector quantity is same as that of what? Direction of flow of current, or you can consider it as the opposite direction of movement of electron also. Now, what about its magnitude? Current density capital J is marked as the current flowing upon the area of cross section. So we just had the expression for current as NA V suffix d into E all divided by A. That is going to give the final expression as N into V suffix d times small letter e. You can have the same formula here as well. And finally, coming to the dimensional formula, it's going to be what? A t raised to minus of 2, and the unit is going to be what? Ampere per meter square. All right, moving to the next, that is mobility. It's nothing, the drift velocity V suffix d applied value of drift velocity attained upon applied value of electric field, and you may have the same in another format, that is small letter e times tau by m. Again, m stands for mass of electron, e stands for charge of electron, and tau stands for average relaxation time. And the next one is Ohm's law. Next is Ohm's law. As you all know that once all the physical conditions remains the same, okay, the current flowing is directly proportional to the potential difference. The same can be explained in another format, that is V is equal to I into R. All right, where capital R stands for the resistance of the conductor, that is represented as capital R. Capital R is equal to small letter m times L all divided by A into N times E square into small letter 2. All right, now here if I consider small letter L and A out, what we have left over here is, just have a look, we have got small letter m there, then we have got small letter n there, we have got E square there, and we are left with tau. This particular thing is known as what? The specific resistance, or that is also known as small letter t, and we will be coming with the same in a few, the slides ahead also. Since we were discussing that particular relation over here, I just wanted to explain that here itself. Next is ohmic and non-ohmic conductors. As the name says, ohmic conductors are those conductors that obeys Ohm's law, and non-ohmic conductors are those which does not obey Ohm's law. For any ohmic conductor, the IV relation is going to be a straight line, and for non-ohmic conductor, it's never going to be a straight line, and here you have got such an example. And next is electric resistance. We just had a discussion of the same over here. The same thing is appearing here as well. Electric resistance is like, if you want to just define that electric resistance, it is the opposition offered against the flow of electron in any conductor. And mathematically, while if you want to get the expression for electric resistance in terms of voltage, I mean potential difference and current, then it could be R is equal to V by I. If you want to get the expression for the same in terms of resistivity, length and area of cross section, then you may have it as R is equal to rho L by A. Alright, now coming to the unit, it is ohm, and while coming to the dimensional formula of that, it's going to be ml square t raised to minus 3 a raised to minus of 2. Alright, moving to the next, that is how the resistance of a wire is going to change if we immediately change the length as well as area of cross section, keeping the volume as constant. I repeat, volume as constant. So here what's going to happen is I am having a resistance of R1. Alright, I am having a resistance of R1 and initially the length was L1. Fine. Now the length is changed to L2. Now the length got changed to L2 and the new value of resistance is going to be what? R2. In that case, how the resistance is going to change is, or how I can mark the relationship between R1 and R2 is R1 divided by R2. I repeat, R1 divided by R2. That's going to be L1 by L2, the all square. And if instead of having the measurement of length, if I go for the measurement of radius, that means R1 was the resistance, and at that time the radius of the cross section, let the resistance be of a cylindrical shape, and the cross section was having a radius as R1, and that got changed to what? R2. Then the resistance got changed as R2, capital R1, R2 for the resistance in the initial and final value, small letter R1 and small letter R2 for the radius of the cross section, then R1 by R2. I repeat, R1 by R2. This particular ratio is going to be small letter R2 divided by small letter R1 all raised to 4. Was that okay? Moving to the next, that is resistivity. Already we had the expression for this. Rho is equal to m upon n into E square times tau, where m is mass of electron, n is number of free electrons per unit volume, E is charge of electron, and tau was average relaxation time. Next is the temperature dependence of resistivity. If rho naught is the resistivity of a given material when the temperature is 0, and if rho suffix t is the temperature is at T, then what we can have is all in degrees Celsius, please note. Then how we can have the relationship is rho suffix T, that means the resistivity at any temperature T, that is equal to rho naught into 1 plus alpha times T, where alpha is known as temperature coefficient of resistivity of the given material. Alright, moving to the next, that is electrical conductivity is nothing, just the reciprocal of specific resistance or resistivity. Okay, and here comes the relationship between current density and conductivity as well as current density, that is J equal to sigma times capital E. Alright, where J stands for the current density, sigma stands for conductivity, and capital E stands for the electric field that we applied. Alright, next comes the combination of resistors. Normally we can have two type of combination. First one is series combination and second one is parallel, and if you go for the combination of both, that's known as series parallel combination, the mixer circuit we can say. So if we are having a series combination, then R equivalent. So here I have got R1, R2 as well as R3 are three individual resistors. Once I connect that in series, the R equivalent value, that is going to be what? R1 plus R2 plus R3. Okay, now about this we need to be informed about few more things. First thing, if I am having a series circuit, then the current flowing through all the resistors, current flowing through R1, R2 and R3, that's going to be the same. And if I need to consider the effective potential difference across A and B, then the effective potential difference across A and B, that is V suffix AB, that is going to be V1, that is potential difference across resistor number 1, plus V2, that is potential difference across resistor number 2, plus V3, that is the potential difference across resistor number 3. So that is very, very important. You need to be very careful about this particular part while solving any circuit, or once you are asked to calculate effective potential difference, or to calculate the potential difference across any 2 points, so and so and so. All right, coming to the next, that is parallel combination. So if we have got three resistors like this, R1, R2 and R3 connected parallel, fine. In this case, R equivalent value, that is going to be what? How to calculate R equivalent value? 1 upon R equivalent, that is going to be 1 upon R1 plus 1 upon R2 plus 1 upon R3. This is how we calculate R equivalent in case of parallel combination. Okay, the way we discussed about the current as well as voltage in this case, in the same manner we need to address the same for this particular electric circuit as well. So in this case, you must know V1 is equal to V2 is equal to V3 is going to be what? Capital V. That means the effective potential difference across the terminal A and B, that is going to be same as that across V1, V2 as well as V3 in case of parallel combination. And if we need to mention about the current flowing, so here if I consider the current as I1, if I consider the current here as I2, and if I consider the current here as I3, and if the net current entering the circuit is treated as I, then I can say that the effective current that was entering over here, that means the current entering over here, if it is marked as I, then I is equal to what? I1 plus I2 plus I3. All right, moving to the next, that is if n number of identical cells are connected in series initially and then they are connected in parallel. Now if I want to calculate the ratio of such a combination, then the resistance once they was connected in series, that is Rs upon once it was connected, if I take it as R suffix P, so then this ratio Rs by Rp, that's going to be n square by 1, or you can simply say that it's Rs upon Rp simply n square. All right, now this is again something very important. What I'm going to have here is, let me consider an arrangement like this. Let me consider an arrangement like this, and let me name this as A, B, C, D, E, F, G, H. All right, all edges of resistance capital R each. Okay, fine. In this way, the entire edges are of resistance capital R. Now, first one, if we consider terminal across the diagonal of the cube, like for example between A and G, or I can say between H and B, diagonally opposite, there it is going to be 5R by 6. It's going to be 5R by 6. And if it is the diagonal of a face, for example, I can say across BG, all right, across FC, or I can say across AH, in that case it's going to be 3R by 4. And if it is along a side, for example along AB or along BC or along CG and so and so, it's going to be 7R by 12. All right, moving to the next, that is electric cell. Fine, you know that this is that particular source of energy that makes this electron flow in an electric circuit. All right, so associated to this, we need to explain two things. One thing is EMF and second one is potential difference. Both has got same SI unit. Okay, both has got same SI unit, that is volt, but there is a small difference. The difference is here it is work done in moving a unit charge round the circuit in a cell, all right. For example, here if I consider this as an electric circuit starting from point A and reaching back to the point A, that is electromotive force or EMF of a cell, work done in moving unit charge around the circuit. And if we consider potential difference, there let this be the positive and let this be the negative terminal, and let this be the external resistance what I am connecting. So a few Coulomb charge is moving from positive terminal, let me take this as A, and it reaching the negative terminal, that is B. So it's not around the circuit, it started from one terminal of the cell and reaching onto the other terminal of the cell. Then work done moving 1 Coulomb charge along this track from A to B between two terminals of the cell, that is known as what? Potential difference. The most important part is potential difference across the terminal is always less than the EMF of the cell for a closed circuit. All right, moving to the next, that is internal resistance. As the term says, it is the resistance offered by the cell itself. And the most important part is here, we must know about the EMF of the cell, terminal potential difference V, current I, and small letter r. How these four terms can be connected. If the cell is being discharged, the relation is going to be E is equal to V plus I into R. If it is discharging, and if the cell is charging, then it's going to be E equals V minus of I into R. If it is discharging, if it is charging, this is the case, and if it is discharging, this is the case. Discharging means discharging of cell. Discharging of cell, charging of cell. Alright, moving to the next, that is grouping of cells. Here also, again, we are having three categories: series grouping, parallel grouping, and mixed grouping. If it is series grouping, where I am having cells of EMF E1, E2, E3, etc. up to En connected in series like this. Effective EMF of the cell, E equivalent, it's going to be E1 plus, E2 plus, etc. up to En. Etc. up to En it's going to be. And the effective internal resistance offered by the cells, you know that this is a series combination, so obviously R equivalent is going to be R1 plus R2 etc. up to Rn. Simple. So if such a combination is connected across a resistance of capital R, then the current drawn from the cell, I need to be the effective EMF, that is E1 plus E2 etc. up to En, all divided by capital R plus R equivalent. Alright, and if you have got identical cells, definitely this is going to be N times E divided by capital R plus N times small letter r. Fine. Now if we are having a parallel combination like this, then E equivalent. So here I am having identical cells, then E equivalent is going to be what? Small letter e only, and R equivalent, that is going to be what? R upon small letter n, isn't it? Then in that case, the effective value of current, in the same case we are having a combination, parallel combination plus capital R resistance connected across, then the effective value, that means the resultant current being drawn from the cell, is going to be E equivalent, that is small letter e, all divided by external resistance plus R equivalent. What is R equivalent? R divided by small letter n. Was that okay? Moving to the next, that is the mixed grouping. That means here I am having n number of series cells, n number of cells connected in series, and m number of such combinations. I repeat, n number of cells connected in series with internal resistance and m number of such combinations. Alright, now the effective EMF is going to be what? N times C, because we are having n in series, so effective EMF is going to be what? N times small letter e. N times small letter e, and R equivalent is going to be N times small letter r, that is the equivalent resistance just because of the cell that connected in series, and we are having m such rows, so N times R all divided by m, that is going to be R equivalent. Alright, so here if I go for R equivalent, there you can see the same expression here, it is NR divided by m. And what was effective EMF? That was N times E. So the that means the resultant current that is being drawn out of the cell is, I need to be effective EMF, that is N times E, all divided by capital R, that is the external resistance that we got connected, plus the effective internal resistance of the combination of the cell, that is N times R, all divided by small letter m. The same expression you can have here as well. Alright, now comes the most important part, that is, if we are expecting maximum current to be drawn from a combination like this, then always remember one thing, the external resistance what we are connecting over here, that is capital R, that need to be same as that of the effective internal resistance of this combination, which was N times R, all divided by small letter m. Was that okay? Moving to the next, that is Kirchhoff law. We have got two laws. First one is junction rule and second one is loop rule. Junction rule is law of conservation of charge and loop rule is law of conservation of energy. loop rule says the effective potential drop across the round in a closed circuit, the effective potential drop across a closed loop, that is always equal to 0. And the junction rule says that if we consider a closed circuit, the total current entering will be equal to total current leaving the junction. All right, moving to the next, that is Wheatstone bridge. Wheatstone bridge is all, like, you know, it's also known as meter bridge, or that is also known as slide wire bridge. Okay, in this case what happens is this particular setup always help us to find out the unknown value of resistance of a resistance wire, or a particular electric component which exactly behaves same as that of a resistor. So if we have got a balanced Wheatstone bridge, that means the one through which the current flowing through this galvanometer is equal to 0. I suffix G is equal to 0 is treated as a balanced Wheatstone bridge. So if we are having such a combination, then P by Q, here you can see P here and you can see Q here, P by Q need to be equal to R by S, provided if it is a balanced Wheatstone bridge, and that particular situation is known as balanced Wheatstone bridge. All right, moving to the next, that is meter bridge. This is exactly, you know, the simplest form of Wheatstone bridge, not balanced Wheatstone bridge, the simplest form of Wheatstone bridge condition. So let us consider this particular arrangement. So this arrangement is known as a meter bridge. Fine. So here you are having your resistance that is connected in gap 1, that is marked as capital R, and the resistance that is connected across gap 2, that is marked as small letter S. Now here you can see galvanometer, and you may mark this particular point where the distance from this particular edge is marked as L1 as the balance point, where the current flowing through the galvanometer is going to be 0. So under this particular situation, we can consider the same circuit exactly as that of what? A balanced Wheatstone bridge. So considering the balanced Wheatstone bridge condition that we discussed over here, once we apply this particular concept exactly onto the given situation, instead of P by Q, I repeat, P by Q, that was equal to R by S in this case, isn't it? So once I apply that over here, I may mark it as R by S. R by S, that is equal to what? L1, it's L1 upon 100 minus of L1. Alright, so in this way, just by measuring the value of L1 and L1 only, we can calculate the value of unknown resistance. If S is unknown here, so obviously I can easily calculate that particular value from here. Next is electrical energy. So the energy is supplied by the source, that means the cell, to maintain the flow of current across a circuit, that is known as what? Electrical energy. So if we apply a potential difference of capital V, and as a result of that a net charge of small letter q is being transferred across the circuit, then the electrical energy being delivered by the source is treated as V into I times Q over there. Alright, so it's V into Q, or in terms of I we want to represent, it can be represented as what? V into I times Q. Alright, and if you want to explain the same in terms of the resistance, we may have it as I square times R into T, or if you want to have it in terms of V, R and T, then you have got another option, that is V square times T upon R. Now, what about its unit? SI unit is Joule. Alright, now there is one more unit of that, that is kilowatt hour, which is another practical unit of what? The energy used over there. And then this same thing, that is kilowatt hour or watt hour, that's also known as what? Board of trade unit, but it's not watt hour, that is kilowatt hour. Alright, now comes few relations. That is 1 kilowatt hour, that is 3.6 into 10 to the power 6 joule, and 1 horsepower, that is 746 watt as well. Alright, okay, now this is about power, and there it was about the energy that you must know. Here this was about power, that is energy delivered in unit time, and there it was in terms of energy. Alright, moving to the next, that is electric power. Nothing, it's energy provided or delivered by the source in unit time, that is known as what? Electric power. So here, if this was energy, this energy upon time, that is calculated as what? Electric power. So in this particular expression, what all the term was there, like V into I into T, then I square R times T, then V square times T upon R. From all these mathematical relations, once T get cancelled, that gives the expression for the electric power. That is P is equal to V times I square times R, and V square times R again. Sorry, V square by R in this case. All right. Now, as I told in the in this particular slide, there was that horsepower as well as watt relation was there. At there itself, I told you this is not the unit of energy, that was of power. The same thing is appearing here. The SI unit of power, that is watt, and 1 kilowatt is equal to 1000 watt, and 1 horsepower, that is 746 watt. All right. Now, next comes the heating effect of electric current, and that is also known as what? Joule's law. All right. So here in these two slides, I was telling about the energy being delivered by the source, or what was the energy that was spent from the end of the source to maintain a steady flow of current of I ampere. Now coming to this one, what this particular thing states is, though the equations part looks the same, just the impact is a bit different. What the impact is, here what happens is, I am having a resistor of resistance capital R, and I am applying a potential difference of capital V, and as a result of that, I ampere of current is being flown through this wire of resistance capital R. Now as a result of this particular wire is going to get heated. Now that heat, capital H, that is equal to I square times R into T, and this is known as what? Joule's law of heating. And if you want to calculate the heat dissipated per unit time, that is again the same as that of power only. That's going to be I square times capital R. Now let me take you to the next chapter, that is moving charges and magnetism. So here, first of all, we will be discussing about what is magnetic field. Okay, it could be the space around a magnet or a current carrying conductor, where the influence of magnet can be experienced. All right, or you can say that it is a space around a magnet or a current carrying where another magnet is going to experience a magnetic force. All right, so the SI unit to represent the magnetic field is Tesla. Okay, and 1 Tesla is 1 Weber per meter square, and in the CGS system, it is represented in terms of Gauss, or it is also represented in terms of Ørsted, and 1 Gauss, that is equal to 10 to the power minus 4 Tesla. This conversion you must never ever forget. All right, now if we go ahead, first comes biot-savart law. As you all know that here it is going to tell you about the magnetic field due to a small current carrying conductor. So that small current carrying, due to that small current carrying conductor, the magnetic field dB, that is going to be mu naught divided by 4 pi I dl sine theta, all divided by what? R square. And you all know that magnetic field, that is a vector quantity, so the direction of that is going to be along dl cross r vector. I repeat, dl cross r vector. Okay, dl cross r vector means dl is in this direction, r vector is in this direction. So here this is r vector. Let me show that with some other color. So here this is dl vector, and here it is r vector. So dl cross r means it is away from you. So here the direction of magnetic field is away from you over here. All right, okay, fine. Now if they are telling us about a charged particle of magnitude q moving with a speed of v meter per second, and if we need to find out magnetic field at any particular point p, which is at a distance of small letter r, at any moment there, this is going to be the magnetic field. That is, it's going to be mu naught divided by 4 pi, okay, into q times v cross r. It's v cross r all divided by rq. In this way also we can calculate the magnetic field due to a moving charge, and here this was due to a current carrying strip of small length dl. All right, moving to the next, here it is magnetic field due to a straight current carrying conductor, and you never miss this. This is a finite wire. That means the length is fixed, and here this angle is phi 1, and here this angle is what? Phi 2. Phi 1 as well as phi 2. In that case, in that case the magnetic field is going to be, see, have a look here, it is going to be mu naught divided by 4 pi. For that one, it has having a finite length, isn't it? So angle is also fixed, so it's going to be mu naught divided by 4 pi I by r into sine of phi 1 plus sine of phi 2. We have the same thing here, mu naught divided by 4 pi I by r into sine of phi 1 plus sine of phi 2. Now if it is an infinite long wire, so here this is going to be sine 90, here this is also going to be sine 90. Sine 90 is 1 plus 1 is 2, so there the same equation get converted to mu naught divided by 4 pi 2 times I by r. Alright, and if it is an infinite long wire, that means one edge is going till infinity going till infinity, and we are asked to find out the magnetic field at any point like this. Okay, the tip of at a perpendicular distance from one edge of the wire. There I can take sine theta 2 as 1 and sine of theta 1 is going to be 0 there. So the same expression again going to get modified as mu naught divided by 4 pi. Here this time it's not going to be 2 times I, it's only going to be I upon r. Alright, going to the next, that is magnetic field at the center of a circular current carrying coil. Okay, now it is at the center of a current carrying coil like this. Okay, let small letter a be the radius and I be the current flowing. In that case, magnetic field B, that is going to be mu naught times I upon 2 times pi into A. Mu naught times I into 2 times pi into A. Alright, and if there are n number of turns, in that case you have to multiply the same term with capital N, or you may mark it as smaller letter n also, never going to make that a huge difference there. Now if I have got an arc like this, that means I am having a current carrying arc like this. Okay, and due to this I need to find out magnetic field at some point somewhere here, and they are provided with the radius of this particular arc as small letter r and this angle as small theta. In that case, here this is going to be the magnetic field, that is B is equal to mu naught divided by 4 times pi into I times theta all divided by small letter r. Okay, due to a current carrying arc subtending an angle theta radian and making a radius of small letter r. Alright, going to the next, this time it is magnetic field on the axis of a current carrying circular coil. Okay, and the point is marked at a distance of small letter r from the center, not r, here it is marked as small letter x from the center. Alright, so here you may mark the magnetic field as B is equal to mu naught divided by 4 pi, okay, I into 2 pi times, alright, here the distance is x and the radius is small letter r, so radius is small letter r means it's going to be 2 pi r square all divided by r square plus x square raised to 3 by 2. Further resolving this, see, you know, it is going to get converted like this. What happens over here is pi and pi will cancel each other, this will cancel each other, or you will get number 2 in the denominator. Alright, so you can have the same expression there, and here this is just due to one loop, okay, one coil, and if I have got n number of turns, the same expression can be multiplied with small letter n or capital N, whatever you prefer, but n or small letter n or capital N is going to be number of turns, that's all. Alright, now if I want to take this point towards the center, okay, that means let point P move towards the center, that is capital O, there definitely small letter x is going to be 0. There you will get the expression as exactly the same thing that you had over here. See, you can see that it's going to be again mu naught times n into I divided by 2 times small letter r. There it was small letter a, radius was marked as small letter a, here radius is marked as small letter r. That is the only difference, rest everything is the same, and this is very important case. There were questions many a times associated to this. Moving to the next, this time it's Ampere's circular theorem. So here this is closed integral of B dot dl along a closed curve, that is going to be what, mu naught times I. This is Ampere's circular theorem, and the applications associated with this one is very important. And here comes the first, that is magnetic field due to an infinite long current carrying circular cylindrical wire. It's circular cylindrical wire. So for the case number 1, here we are going to have small letter r greater than capital R. I repeat, small letter r greater than capital R. All right, that means we are going to have a point outside the cylinder. Okay, outside the cylinder, not even on the surface of the cylinder, again far away from that. So in that case, the magnetic field is going to be B equals mu naught times I divided by 2 times pi into R, where small letter r is the distance from the center. I repeat, it is distance from the center, and I is the current passing through that. Now, if the cylinder is something like this, where I can find a space. Okay, let me create it like this. If the cylinder is something like this, okay, that means here only this, through this portion is current passing, the rest, I mean inside portion is a hollow like structure. Okay, it's a hollow cylinder. Then in that condition, if I need to consider any point inside, so you must understand, see the structure is, let me redraw the same structure over here. So the current flowing is only through this particular portion. Its inside portion is cavity. In that case, the magnetic field inside any point is going to be what? 0, because we don't have any current flowing inside that cross-sectional area. Okay, so it's just going flowing through. So it's something like this. It's something like this. If you take a piece of paper and just fold it so that it can make a pipe-like structure or cylinder-like structure, exactly the same thing is happening here. All right. So this, since this space belongs to some other topics, I need to delete this one. And now comes the next, that is inside a cylinder where current is uniformly distributed. That means this time, you know, the current is even flowing through the cross section. So this time it's a solid cylinder, not a hollow cylinder. I repeat, this time it's a solid cylinder, not a hollow cylinder. So in that case, the magnetic field is going to be mu naught divided by, it's going to be mu naught divided by 4 pi, okay, into mu suffix r, where mu suffix r is relative permeability of the substance of the material out of which this particular cylinder is now made. So it's mu naught divided by 4 pi, okay, into mu r times, okay, 2 times I into small letter r, all divided by capital R square, where capital R is the radius of the cylinder and small letter r is the distance from which you know, we are just taking that what you can say, the point. I think I wrote mu r here. That's not mu r. Yes. Sorry. It's mu r only. Relative permeability. All right. Okay, fine. Now I thought, you know, it's mu times a small letter r, so that was a small error. So it need to be mu suffix r relative permeability. The rest all is the same. Okay, so what I was telling, you know, that small letter r, that is distance from the cross section. Okay, so here this is capital R, and here I can mark this as small letter r, the distance from the center. All right, so that was all about the magnetic field due to a solid cylinder having a relative permeability of the material as mu suffix r. Now moving to the next, that is magnetic field due to a solenoid. Now if we are considering a long solenoid and we need to find out the magnetic field at the center, then the general expression is B is equal to mu naught n times I. And if you are finding out the magnetic field at one of its edge, like since if this is the long solenoid, okay, like this, let this be a long solenoid, and if you are finding the magnetic field at the center, then it's going to be mu naught times n into I. And if you are finding out it one of its edge, then it's exactly going to be the half of this, that is mu naught n times I by 2, where n is number of turns per unit length and I is the current flowing through the wire that we have just wound across that cylindrical structure. All right, now next is force acting on a charged particle moving in a uniform magnetic field. So if we are having a charged particle Q entering into a magnetic field, okay, making an angle 90 degree with respect to the magnetic field, then the force experienced is F is going to be Q into V into V. All right, perpendicularly. And if it is making an angle theta, then we may have the general expression as F is equal to Q into V cross B. Okay, so V cross B is going to be F is equal to Q into VB sine of theta. All right. Okay. So now, in order to find the direction, we may use Fleming's left-hand rule. That is FBI. That means here F stands for the force, and here B stands for the magnetic field, and I stands for the direction in which the charged particle was moving. So exactly the same. You may have it over there. All right. Okay. Fine. Now, moving to the next. That means if the charged particle is moving into a magnetic field like this. If a charged particle is perpendicularly entering into a magnetic field like this, okay, so definitely as per Fleming's left-hand rule, FBI, a force need to be acting in the upward direction. So here it will be following a circular path like this. So it's very clear. Since it is following a circular path, definitely we need to tell about the radius. So this time the radius of the charged particle is going to be a small letter r. That is equal to m into v all divided by b into q, where m is mass of the charged particle, v is the velocity by which it was entering, and b is the magnetic field strength, and q is the charge that is being carried by this positive charged particle. Don't forget, here this was a positive charged particle moving, and if it is a negative charged particle, the direction will be getting reversed, and if the rest all other parameter remains the same, radius is also going to be the same. And now I told you this is going to move in a circular path, so definitely since it is moving in a circular path, that particular path, the motion is going to be a periodic motion. Fine. Then we need to consider about the time period also. So the time period of that circular motion, capital T, this time it's going to be 2 pi m all divided by b into q, and the frequency of that motion f, that's going to be bq divided by 2 times pi into f. That's also again an important relation. Moving to the next, that means here if the charged particle, again instead of perpendicularly entering like this, if the charged particle is entering the magnetic field by making an angle theta with respect to magnetic field, the magnetic field. Now velocity component, we are going to have two velocity component. One is along the direction of magnetic field, that is going to be v cos of theta, and another one is going to be perpendicular to the magnetic field, that is v sin theta. Two velocity components are going to be there, that is v cos theta and v sin theta. V cos theta is in the same direction of magnetic field, and v sin theta is going to be perpendicular to the magnetic field. In that case, you know, the radius of the particular path is going to be changed. This was the case where it was perpendicularly entering. Now here this is the case where it is entering at an angle theta. So the perpendicular velocity component was what? V sin theta. The perpendicular component of velocity perpendicular to the magnetic field was v sin theta. So while calculating the radius, I repeat, while calculating the radius, small letter r is going to be, there it was mv sin theta. Sorry, there it was m into v divided by bq. So here it is going to be mv sin theta divided by bq. This is again an important area. Alright, so there it was mv divided by bq, and here it is what? Mv sin theta divided by bq. But time period, it's going to be the same thing only, that is 2 pi m divided by bq. So since time period is not going to change, the frequency also will be the same. That is again a super important area. Now comes the last one, that is the pitch. Okay, I told you here the charged particle was entering at an angle theta with respect to the magnetic field. Alright, at an angle theta with respect to magnetic field. So it will be having two velocity components. I told you v sin theta, that is perpendicular to the magnetic field. So here this is magnetic field B vector. Okay, here this is v sin theta, and here this is v cos theta. If anybody find it difficult to visualize, just have a look. This was the magnetic field. Okay, alright, and the charged particle was entering like this, v. So here this was a magnetic field, so this angle is theta. So here this is going to be v cos theta, and here this is going to be v sin theta. Alright, and you know this particular case, in this particular case, how to visualize this one is, here this was the magnetic field, here this was the magnetic field, and charged particle was entering like this. This was what I was telling, charged particle entering perpendicular to the magnetic field, and here it is making an angle theta with respect to the magnetic field. So now you may see that here this is v cos theta. By mistake I wrote this as v sin theta. Here this need to be v cos theta. Now how the path is going to be, it's going to be helical one. That means earlier the charged particle was moving like this. Alright, in which case? In this case the charge particle was moving in this manner. Now for this one, the charge particle is moving like this. So it's following a helical path. Am I right? So that helical path, see, it's starting from here and reaching here. See, just look, have a look at this. So this much distance it is traveling, and that distance is known as what? The pitch. It's known as what? The pitch. So there you may calculate that pitch as 2 pi. Okay, what was the time period? It was 2 pi m. It was 2 pi m divided by bq into this particular velocity component was what? V cos theta. V cos of theta. V cos of theta. V cos theta. So the pitch is 2 pi m by bq, that is time period, multiplied by the velocity component in the same direction of magnetic field, that was V cos theta. Moving to the next, that is motion of a charge particle in a combined electric and magnetic field, which is also termed as Lorentz force, the resultant force. So this time I am going to have the charge particle in magnetic field as well as electric field all together. So definitely it is going to experience the electrostatic force plus it's going to experience the magnetic force. That's what is represented over here. F is equal to Q into E vector plus V cross B vector. All right, now if the charge particle, okay, if magnetic field as well as the charge particle, they are in the same direction. They are in the same direction. I repeat, magnetic field as well as the charge particle is entering in the same direction. In that case, what happens, V sin theta term is going to be 0. At that condition, magnetic field is not going to be there, only electrostatic force will be acting. Then in that condition, I can say that the force is equal to m into a, that is going to be what? Q into E only. In that case, the acceleration experienced by the particle, small letter a, that is going to be Q times capital E all divided by small letter m. Alright, I told you F suffix B is going to be what? 0, because the charge particle was entering parallel to the magnetic field. Theta is 0, so sin theta is going to be 0 value. Alright, now in that case, definitely the charge particle will be moving with an acceleration, and the path, I repeat, the path is going to be a straight line. Alright, now comes the next, that is, what if we are having electric field as well as magnetic field perpendicularly? So if the electric field as well as magnetic field is perpendicular, then the resultant force acting is going to be what? 0, which means the acceleration is going to be 0. Alright, which means F suffix E as well as F suffix M can be 0 in that case. Alright, then since the resultant force is 0, that means the charge particle is going to be in equilibrium condition. That means it can move in a straight line with a constant velocity. Okay, this is the working principle behind the velocity selector as well. Okay, so I repeat once again, here the electric field as well as magnetic field is perpendicular. So we can be adjusted in such a way that F suffix E, I repeat, we can be adjusted in such a way that F suffix E as well as F suffix B are going to be equal and opposite. There, the resultant force experienced by the charge particle is going to be 0, and we can have the charge particle move with a constant velocity. Okay, with a constant velocity, and this is the working principle behind the velocity selector. Moving to the next, that is force on a current carrying conductor in a magnetic field. If I am having a current carrying conductor of length L through which I ampere of current is flowing, and that is kept at an angle of theta with respect to the magnetic field, then the force experienced by that conductor F suffix B, that is going to be I into L cross B. So this is a general expression. In scalar form, we may have it as I into L B sine of theta. Alright, so here you can see this particular arrangement is kept at an angle theta with respect to the magnetic field. So the one thing that you must know is this is L vector, and L vector is taken in the same direction of current, that you never forget. And here this is the magnetic field, and this angle is marked as theta. Alright, moving to the next, that is force between two infinitely long parallel current carrying conductors. If I am having two long current carrying conductors of length L, alright, and here the current passing is I1, and here the current passing is what? I2, the length is marked as L. Current is in the same direction. I repeat, current is in the same direction. So if the current is in the same direction, it's going to be attractive. So here this is force acting on 1 due to 2, and here this is going to be force acting on 2 due to 1. Magnitude of both is going to be the same, and if I just mention the magnitude, then the force is going to be mu naught divided by 4 pi, okay, 2 times I1 I2 all divided by R times L. Further solving this, here it's going to be mu naught divided by 2 pi I1 I2 all divided by R into L. Alright, if I take this L towards left, so here this is going to be force acting per unit length. That can be the same thing only, but can be represented in a different format like small letter f is going to be mu naught divided by 2 times I into I1 I2 all divided by R. I told you if the current is in the same direction, the force is going to be attractive, alright, and if it is in the opposite direction, it's going to be repulsive. That's also mentioned here. The force is acting, force is attractive if the current in the current in both the conductor is in the same direction, and repulsive if it is in the opposite direction. So that is also an important point over here. Moving to the next, that is magnetic force between two moving charges. I repeat, magnetic force between two moving charges. So here I am having a charged particle Q1 moving with velocity V1 and another charged particle, that is Q2, moving with velocity V2, and we may consider it in this way. Q1 is here, it's moving with velocity V1, and here I am having Q2 and there it is moving with the velocity of V2, and the distance of separation between their perpendicular velocity, so the velocity components, they are parallel to each other, and the perpendicular distance between V1 as well as V2 is marked as small letter r. In that case, the force experienced F, that is going to be mu naught divided by 4 pi, okay, into Q1 into V1 into Q2 into V2 all divided by R square. The same thing is represented here. Alright, moving to the next, that is magnetic dipole. If you are having a current carrying coil through which I ampere of current is passing and small letter r is the radius of that coil, then the area of this circular coil is going to be pi r square. It's just a coil, so area is pi r square. Now I times pi r square. I times pi r square is termed as the magnetic moment, and if we have smaller n number of turns or capital N number of turns, whatsoever it may, then the resultant magnetic moment is going to be I into pi r square times N. Alright, moving to the next, that is torque experienced. If you are having a coil which has got n number of turns, area of cross section is capital A, I ampere of current is flowing, and it is kept in a magnetic field of capital B, where area vector is making an angle theta with respect to the magnetic field, then the torque experienced is NBIA times sine theta. Alright, the torque is maximum when theta is 90 degree and minimum when theta is 0 or 180. Moving to the next, moving coil galvanometer. You know about the structure and working and all. At equilibrium condition, we know that the torque experienced by the coil, that is going to be the torque offered by the spring. So that is the basic principle behind how to calculate the current and all, how to sense the current and all, and later on how to measure the current, in fact, by converting that into a meter. So at equilibrium condition, we know that NIB into A, that is equal to what? K times theta. Fine. So from here I can say that current I, that's equal to what? Current I is going to be K divided by N times B into A times theta. So I can say that the deflection over here, okay, it's directly proportional to the current passing through this one, and that is the the principle behind moving coil galvanometer. And from there, how to we can measure the current, not measure the galvanometer, actually sense the current only, but we can later on convert that into ammeter to measure the value of current as well. So here I think I must tell about what all these terms do stands for. Earlier I told you N stands for number of turns, I stands for the current flowing through, and B is the magnetic field strength of the radial magnetic field what we maintain for this moving coil galvanometer, and capital A is the area of the coil that we are having inside, and K, that is the restoring torque per unit twist. That is again that property related to the spring that we have, and theta is the angle through which the coil got turned or the spring got twisted, we can say. Both are the same. Now moving to the next, that is current sensitivity as well as voltage sensitivity. So basically the sensitivity means what is the angle through which the coil got turned or the spring got twisted per unit value of current or per unit value of voltage. If it is for unit value of current, that is known as current sensitivity, and if it is for unit value of voltage, then it is known as voltage sensitivity. So twist per unit value of current, the angle through which this got twisted for unit value of current, that is theta by I, that is known as current sensitivity. So there it is going to be NBA divided by K. All right, and if we are considering about voltage sensitivity, so again it is theta divided by V. There you may have the expression as NBA divided by K into R, where R is the resistance. Here they have marked it as small letter r, never makes any difference. So I prefer resistance to be capital R, so that's what it's mentioned over here. Now comes something very, very important. How to have a more sensitive galvanometer. How to have a more sensitive galvanometer? You must have large number of turns. Okay. Second, B should be large. Third, capital A should be large, and K should be small. All right. Moving to the next, that is conversion of galvanometer into ammeter. In the next page, we are having conversion of galvanometer into voltmeter. So to convert a galvanometer into ammeter, you know that ammeter is always connected in series to the circuit. So we must have almost zero resistance, otherwise it will completely alter the circuit. So in order to do that, galvanometer having resistance capital G must be shunted with a resistance of small value. All right, so this is how we convert galvanometer into an ammeter. The same thing you can show here. And what value of small resistance need to be connected parallel to the galvanometer so that this particular design can measure a current up to I or I max. It can measure a current up to I max. All right, there S value is going to be I suffix G, that is the maximum deflection current of galvanometer, all divided by I max minus of I suffix G into capital G. So this is the value of small resistance that we are going to connect parallel to the galvanometer so that I can convert a galvanometer of resistance capital G to an ammeter that can measure a maximum current up to I max. All right, here comes the conversion of galvanometer into a voltmeter. We know that voltmeter we will be connecting across a particular resistance across which we need to measure the potential difference. So this is that particular resistor across which we need to measure the resistance. So here it is marked as capital R. This resistance is marked as capital R, and the resistance that I am going to connect, let me mark it as X. There it is marked as capital X. All right, so let me make that change so that you guys are never going to get confused with that terms. So here let me mark it as X, and let me mark it as capital R. So across this there is a particular voltage drop, and let that be the maximum value of potential difference that we are going to measure using this particular arrangement. So V max need to be the potential difference across here. So once this galvanometer is showing the maximum deflection, the current flowing through this one need to be what? I suffix G, the maximum deflection current. So V max here, see, have a look. V max, that means exactly the potential difference over here. It's going to be the summation of potential difference across the galvanometer and the resistance that we connected parallel. And you know, we can't connect simply a resistor over here. It must be very large so that the current flowing through this one need to be minimized. That means from the main circuit, we are going to draw a minimum value of current so that it's not going to create a very huge impact on the circuit. Otherwise, the complete things will change. So anyhow, if I consider the voltage to be same across these two, that means across capital X as well as this GR combination, then V max is going to be what? V max is going to be I suffix G into capital G, that is the voltage drop across this galvanometer, plus I suffix G into capital R. All right, so if I need to calculate the value of I's capital R over there, so I can take this towards the left. So here this is going to be what? V max, okay, V max minus of I suffix G into capital G, that's going to be I suffix G into capital R. Now let me take this, let me divide this entire term with I suffix g. That gives me the final answer as V max all divided by I suffix g. Okay, V max all divided by I suffix g minus of capital G is going to be capital R. So this is that resistance that we are going to connect in series to the galvanometer. Alright, so you may see the same expression here as well. Alright, so that was all from the recap video of physics for your first examination. Now prepare very well and try to solve maximum number of questions. This stuff was more than enough for you to go through the theoretical part. Now please focus on your numerical practice. Make yourself as much strong as onto the numerical area. Now prepare well, do your best. Happy learning.